Students, we will continue the topic hemoglobin, competition number 6.11, and subtopic is functions of hemoglobin. Structure of hemoglobin we have already discussed. Three major functions of hemoglobin are: first is carbon dioxide transport, oxygen transport, and hemoglobin act as a buffer. First we will study about transport of carbon dioxide by hemoglobin. At rest in our body, near about 200 ml of carbon dioxide is formed in tissues due to various metabolism in an adult. This carbon dioxide is carried out by following three ways. First is called as isohydric transport of carbon dioxide. Second, in the form of carbaminohemoglobin, and third is in soluble form. By these three forms, carbon dioxide is transported from tissues to the lungs. So this is the tissue cell I have shown here on metabolism. Inside the cell, carbon dioxide and water is formed. From the cell, this carbon dioxide enters into the blood. 10% of the carbon dioxide dissolve in the blood and 90% of the carbon dioxide enters inside the RBC. This 10% is transported as a dissolved form, and out of 90% which has entered in the RBC is transported in two forms: 75% by isohydric transport and 15% in the form of carbaminohemoglobin. First, about the isohydric transport of carbon dioxide, just I have told you 75% of the carbon dioxide formed in the tissues are transported by this system. At the tissue where pH is low and there is high PCO2 concentration, this favors conversion of carbon dioxide to H2CO3 by combining with water. Here the most important enzyme required for this reaction is carbonic anhydrase. Now this H2CO3 is then broken down into H plus and bicarbonate ion, again catalyzed by the same enzyme, that is carbonic anhydrase. Now this H plus ion, if they remain free inside the RBC, they tend to decrease the pH of RBCs. Therefore, these H plus ions are readily taken up by deoxyhemoglobin to form HB. This is called as Haldane effect. Now, the bicarbonate ions, which are comparatively larger in size, moves out of RBC into the blood with their charge. To maintain the electrical neutrality, same number of chloride ion enter inside the RBCs. This is called as chloride shift or Hamburger effect. Now coming to the Haldane effect, I have told you H plus ions are taken up by deoxyhemoglobin. In this deoxyhemoglobin, H plus ions are neutralized by the imidazole group of histidine, which is present in the globin chain of hemoglobin. So this reaction occurs at tissues. Now when these RBCs goes to the lungs, where the conditions are different, here the pH is high, also partial pressure of oxygen is also high. Due to these two factors, HB release the H plus ion and combines with oxygen to form oxyhemoglobin. Now this H plus ion now becomes free. To neutralize these H plus ions, bicarbonate ions which are present in the blood or plasma enter inside the RBC. To maintain the electrical neutrality, chloride ions shift outside the RBC, which is called as reversal of chloride shift. Now this H plus ion and bicarbonate ion combines to form H2CO3. Again the enzyme is carbonic anhydrase. This H2CO3 breaks into water and carbon dioxide. Now this carbon dioxide which is formed inside the RBCs diffuses out of RBC and it is expelled by the lungs. Whatever happens in the tissues, the reverse of that will happens at the lungs, and this is because of different conditions prevails in the tissues and in the lungs. This is called as isohydric transport of carbon dioxide. Next is transport of carbon dioxide in the form of carbaminohemoglobin. 15% of the carbon dioxide is transported by combining with N-terminal of hemoglobin molecule as shown in the reaction to form carbaminohemoglobin. So, globin chain, it is a protein. So, all of us know that each protein has two ends, amino terminal which is also called as N-terminal and carboxyl terminal or C terminal. At the N-terminal, amylo group is free. So, carbon dioxide combines with this N-terminal to form carbaminohemoglobin and transported through the blood. Last type of transport is transported in the form of dissolved form. 10% of the carbon dioxide is transported in dissolved form. Here 10% of the carbon dioxide which have not entered into the RBC remains in the blood, combines with water to form H2CO3. The enzyme is carbonic anhydrase. With this H2CO3 is broken down into bicarbonate and H plus ions. Now here again H plus ions are formed. This H plus ion tend to decrease the pH of the blood, but these H plus ions are neutralized by the buffer system present in the plasma. So we have seen 75% of H plus ions are neutralized inside the RBC by hemoglobin molecule, whereas only 10% of H plus ions are neutralized by the buffer system present in the blood. So hemoglobin is strong buffer as compared to the plasma buffer system. Next function of hemoglobin is transport of oxygen. Each hemoglobin molecule which has 4 subunits combines with 4 oxygen molecules, which is also called as oxygenated hemoglobin. Iron is present in ferrous state. Normally, if 15 gram % of hemoglobin is present, then this 15 gram, each gram combines with 1.34 ml of oxygen, so that 15 gram of hemoglobin in 100 ml can combine with 20 ml of oxygen and transport it. Now these are few things. First, in vitro. In vitro means outside the body. It is observed that when PO2 is 100 mm of Hg, then hemoglobin saturation of oxygen is 97%, and when PO2 is 40 mm of Hg, hemoglobin saturation of oxygen is 75%. Why 40 mm of Hg and 100 mm of Hg is choose? Because 100 mm of PO2 present in lung alveoli, whereas 40 mm of Hg PO2 is present at tissue level. So this is a study carried outside the body. In this study, what we have observed, when the PO2 decreases from 100 mm of Hg to 40 mm of Hg, the hemoglobin saturation decreases from 97% to 75%. Hemoglobin saturation means how much hemoglobin molecule combines with oxygen. That means 22% of the oxygen is released from hemoglobin outside the body. But the same study, when we observed inside the body, when PO2 is 100 mm of Hg, Hb saturation is 97%. When PO2 is 40 mm of Hg, Hb saturation of oxygen is 60%. So if you see this, when Hb saturation falls from, when PO2 falls from 100 mm of Hg to 40 mm of Hg, the hemoglobin saturation of oxygen falls from 97% to 60%. That means 37% of oxygen is released by the hemoglobin to the tissues. Whereas in the outside the body, only 22% of the oxygen is released by hemoglobin at the same pressure or PO2. If you plot a graph on x-axis, we have to take partial pressure of oxygen. On y-axis, we have to take hemoglobin saturation of oxygen. This is the graph of oxygen. This graph is called as oxygen dissociation curve, which shows how oxygen is separated from hemoglobin at tissue. So this is the graph of in vitro study. Here we found a straight line graph, but the same graph, when you study, when you plot a same graph by taking the same pressure in the body, the graph is S shape or sigmoid shape, because more oxygen is delivered by the hemoglobin to the tissues. Now we will study what are the factors which affect the oxygen dissociation in the body. The first and most important factor is presence of 2,3-bisphosphoglycerate or BPG in the body. This 2,3-BPG is absent in vitro, outside the body. So now this 2,3-BPG binds with 143rd histidine and 82nd lysine residue in beta chain. After binding with the beta chain, this 2,3-BPG decreases the affinity between hemoglobin and oxygen molecule. Therefore, oxygen can be easily detaches or dissociated from the hemoglobin and delivered to the tissues. This 2,3-bisphosphoglycerate has less half-life, so it is constantly synthesized and metabolized in RBCs by glycolytic pathway. Now this curves again same oxygen dissociation curve. In the middle it shows the O2 dissociation curve in normal patient when the concentration of 2,3-BPG is normal. But when the concentration of 2,3-BPG increases, for example in anemia or in hypoxia, we have seen that oxygen dissociation curve has shift to the right or to the lower side. That means more oxygen is delivered by the hemoglobin to the tissue, because tissue requirement is increased. If you see the upper curve or left sided curve, where the concentration of 2,3-BPG is less. When the concentration of 2,3-BPG is less, the oxygen dissociation curve has shifted to the left. That means it has dissociated less oxygen to the tissue, or hemoglobin have released less oxygen to the tissue. The next factor which affect oxygen dissociation curve is Bohr effect. At the tissue level, the pH is low because H plus ion concentration is high. Also there is increased values of PCO2. These two condition favors the release of oxygen from hemoglobin to the tissues. So these curves, again, three curves are there. Central curve is at pH 7.4. When pH decreases, that means when H plus ion concentration increases, when pH is less than 7.4, the curve shift towards the right, so that more oxygen is delivered to the tissues. In case of alkalosis, when pH is more than 7.4, the curve shift to the left and less oxygen is delivered to the tissues. Third factor is homotropic effect or heme-heme cooperation or heme-heme cooperativity. First I will explain this heme-heme cooperativity at lungs. When deoxygenated hemoglobin reaches the lungs, all of us know that each hemoglobin has 4 subunits. In the beginning, the affinity between hemoglobin and oxygen is 1 time. The affinity between deoxyhemoglobin and oxygen is 1 time. So in the lungs, due to high PO2, one oxygen molecule binds with one subunit of hemoglobin. When this first oxygen molecule binds with one subunit of hemoglobin, the affinity between the other 3 subunits and oxygen becomes twice, and they easily combines with oxygen molecule in the lungs. When the second oxygen molecule combines with the second subunit of hemoglobin molecule, suddenly the affinity of remaining 2 subunits increases by 4 times. And when the third oxygen molecule binds with the hemoglobin subunit, third subunit, then you find that the affinity of the last subunit with oxygen increases to 18 times. That means when the hemoglobin binds with oxygen, the affinity goes on increasing. This happens at the lungs. The reverse will happen at the tissue level. When this Hb-2 goes to the tissue, one of the subunit releases the oxygen to the tissue. Suddenly, the remaining 3 subunit loses their affinity towards oxygen and they start giving oxygen to the tissue, so that 4 more oxygen molecules can be delivered to the tissue easily. This figure shows when there is no oxygen binding with the hemoglobin, that is called as deoxyhemoglobin, salt bridges exist between the hemoglobin subunits. 4 salt bridges are there. When one oxygen binds with the hemoglobin, any one hemoglobin subunit, one of the salt bridge is broken down. When second subunit of hemoglobin binds with the oxygen, second salt bridge is broken down. When third oxygen binds, third salt bridge is broken down. When fourth oxygen binds, all the 4 salt bridges are broken down between hemoglobin subunits. Now this form of hemoglobin is called as relaxed form or R form. The deoxy form is called as tight form or T conformation. Now there are some causes of shift of oxygen dissociation curve to the right. shift of O2 dissociation curve to the right means it will deliver more oxygen to the tissues. The causes of shifting of O2 dissociation curve to the right are anemia, high altitude, fever, exercise. If you see, in all these conditions, the requirement of oxygen by the tissue increases. Therefore, to fulfill the requirement of tissues, the oxygen dissociation curve shifts to the right and delivers more oxygen to the tissues. When oxygen dissociation curve shifted to the left means it delivers less oxygen to the tissues at that PO2. The causes may be hypothermia, presence of HbF. HbF means fetal hemoglobin. Why? Because whenever fetal hemoglobin is present, if you remember, fetal hemoglobin has 2 alpha chain and 2 gamma chains. Therefore, 2,3-BPG, 2,3-bisphosphoglycerate does not binds with hemoglobin F because 2,3-BPG binds only with the beta globin chain, and this beta globin chain is absent in HbF. Due to absence of this 2,3-BPG, hemoglobin F has more affinity towards oxygen and hence it delivers less oxygen to the tissues. Now, adaptation seen at high altitude. Whenever you go to high altitude, then after few days you will see there is increase in the number of RBCs, which is called as polycythemia. Then there is increase in the concentration of hemoglobin inside the RBCs. Also, there is increase in the levels of 2,3-bisphosphoglycerate in the RBCs, because at high altitude the partial pressure of oxygen is less. Now there are some questions. What is the relation between hemoglobin concentration and 2,3-BPG levels in the blood? So they have inverse relationship between hemoglobin concentration and 2,3-BPG. Next question. Predict the changes in the levels of 2,3-BPG with reason in pulmonary and cyanotic cardiac diseases. Pulmonary diseases means where the alveoli are damaged and oxidation of hemoglobin is hampered. Normally 97% of hemoglobin is saturated in the lungs, but in case of pulmonary diseases and cyanotic cardiac diseases, hemoglobin saturation decreases because diffusion through the alveolar membrane is hampered. So in chronic pulmonary disease and cyanotic cardiac diseases, 2,3-BPG levels increases, so that more amount of hemoglobin, more amount of oxygen can be delivered to the tissues in such conditions. Next question. Predict the levels of 2,3-BPG in acidosis and alkalosis along with shift of oxygen dissociation curve. That I have already explained. The red RBC's 2,3-BPG level is decreased in acidosis and increases in alkalosis. Therefore, ODC, oxygen dissociation curve, is shift to the right and to the left respectively. Now, a patient had road accident and there is loss of large amount of blood. After cross matching, he was treated with massive blood transfusion, but suddenly he develops symptoms of hypoxia. The question is, what is the cause of hypoxia? Predict the oxygen dissociation curve shift. Whenever there is a transfusion of large amount of stored blood, in that stored blood, the levels of 2,3-BPG are less. Therefore, hemoglobin saturation is normal in the lungs, but that hemoglobin does not delivers oxygen to the tissues in required quantity, in sufficient quantity. Therefore, patient develops hypoxia due to lack of 2,3-BPG and oxygen dissociation curve shifted toward left. What is the role of 2,3-BPG here? 2,3-BPG decreases the affinity between hemoglobin and oxygen. When 2,3-BPG is absent, hemoglobin more tightly binds with oxygen and it does not delivers the required amount of oxygen to the tissue, or it will delivers less oxygen to the tissues, due to which there is hypoxia. So these are the three factors which helps to deliver more oxygen to the tissues and gives sigmoid shape to the oxygen dissociation curve. They are presence of 2,3-BPG, Bohr effect and heme cooperativity. Next is hemoglobin as a buffer. All of us know buffer means a system which resists the change in pH, and good buffer means which can neutralize small amount of acids or base equally. Therefore, they possess a group which donate the H plus ion, and also they possess a group which accept the H plus ion in equal quantity. Amino acids have two ionizable groups. One is amino group and another is carboxyl group. At acidic pH, all the amino groups are ionized and the amino acids have positive charge. Now pKa. pKa means in acidic range of pH, we have to adjust the pH in such a way that the half of the carboxyl group are ionized and half of the carboxyl group should be unionized. The pH at which this exists is called as pKa. Now see at pKa, when OH minus or alkali is added or base is added, then that base OH is neutralized by the unionized carboxyl group by donating the H plus ion. Similarly, when H plus ions are added, then ionized carboxyl group should accept that H plus ion and neutralize. Therefore, at pKa, carboxyl group can act as a buffer. At basic pH, the opposite happens. All carboxyl groups are ionized. Therefore, in basic range of pH, again we have to adjust the pH in such a way that half of the amino group should be ionized and half of the amino group should be unionized. The pH at which this exists is called as pKb. So at pKb, when we add alkali externally, then that ionized amino group donates its H plus ion and neutralize it. If we add H plus ions, then the unionized amino group should accept that H plus ion and neutralize it. So in this way, the amino acids act as a good buffer at pKb. So each amino acid should have two pK values at acidic pH and at basic pH. Some amino acids have extra functional group. Example, histidine, which has imidazole group, which ionizes at pH 5.8. So such groups also act as a buffer at various pH. So such amino acid possess three pK values. One pK value of carboxyl group, one pK value of amino group, and one pK value of the extra functional group. Now this imidazole group of histidine has pK value 5.8. So it acts as a buffer at pH in a range of 5.8 plus or minus 1. The pK value of imidazole group of histidine is nearer to our physiological pH of blood, that is 7.4. Hence, at physiological pH, only imidazole group of histidine act as a buffer. Other amino acids have pK values away from the physiological pH of the body. Therefore, they does not functions at the pK values. Only imidazole group of histidine can act as a buffer at physiological pH. Hemoglobin molecule contains 38 residues of histidine and hence it acts as a buffer at physiological pH. This is about the functions of hemoglobin. Thank you very much.